Hello everybody, I am the Draft Doctor. Today's layout is quite advanced. Um, we are looking at an asymmetrical Y branch today. Asymmetrical meaning that one side is completely different from the other. We got to make them both work. Um, Half the problem or half the difficulty of laying out an asymmetrical Y branch is developing a working drawing that we can use to lay out the pattern. Now, I have gone ahead and I've laid out my 6-inch opening. I've laid out my 10-inch opening and my 5-inch opening, and I have connected the center lines at 45 degrees. I have a 10-inch height that I've laid out here, 10 inches to my center line. So quite simply, I lay out my base diameter, a 45-degree angle and a 60-degree angle. I lay out my heights, and my intersection point is now where that miter is going to be. On the 6-inch side, I quite simply laid out the top, my 8-inch offset, and then connected the lines with a 60 and a perpendicular. Now, to have even flow on a fitting like this, we have to locate the center rise here, or the sector height, with a few basic geometric principles. It is a little extensive, but it's also fairly simple. I'm going to start with this 5-inch round, and we'll put a profile on there. Profile meaning just gives me a view of half of the round. Oops. Will give me a view of half of the round, and show me where the element lines are going to land on that. But we always divide our pieces into 12 equal parts, so I've got 6 spaces now on this. Now, to make this have a nice even airflow, I'm also going to put the round profile at the intersection point. And what we're going to do is use parallel lines and points of tangency to find this miter. Now, because this is such an extensive layout, I am only going to lay out 1/2 of this fitting. So on the other side, I would have put a profile here as well, divided it up, and I would also have to put the 6-inch diameter at the miter so I can find its miter. Now, I need both sides of this so I can find my sector height. Here's how simple this is. If I connect my points of tangency from my 4-inch diameter, tangent to the circle here, and we will draw a tangent to the circle here as well. Now I'm also going to draw from my 10-inch tangent to the mitered circle, which is right here, very lightly, and that gives me a point right there, which is 1 point for my miter. And if I just go through the center now, I will find the other point for my miter. Now, we're also going to do the same on the 6-inch round side, tangent to the circle here. I will drop down tangent from my 6-inch round, tangent to my circle there to find part of my miter. I'm also going to draw down tangent from the circle here, tangent to the circle, and now we've got everything except where is my sector. There's 2 ways to find a sector height. If it is a symmetrical Y branch and your sector is perpendicular to the base, you can easily use a 1.5 times the radius, which is designed to give you an even flow. Now, when we have an asymmetrical, we have to use the points of tangency. Now, once again, I'm just going to very lightly put in a profile of my 10-inch round at the base. I'm also going to draw it down here because I'm going to need this for my layout eventually anyways. So let's just draw that on there. Nice and dark there so we can see it. Now, if I connect the points of tangency from this circle to this circle, I get my miter from this circle through there to this circle. And now I'm going to draw tangent to this circle here and to the profile I have at the base. And when I connect those dots, these points of tangency are now going to give me my fitting. So let's start with here. And I'm just going to darken this in. This now is the outside of my fitting. Here is my miter on this. Don't be alarmed that it doesn't go through the center. After all, it's not the center we used, it's the point of tangency that we used. Here now is my branch. And here, to the midpoint here, is my sector height. So there I have half of the Y branch, and let's just mark the other half in so we can see the whole picture. And now we have our working drawing. And if you take a look at the fitting once it's made, this is exactly what you'll see from the side. 10-inch round, 5-inch round, 6-inch round, 8 inches offset from the center, and at the proper height of 12 inches. Here I have a 10-inch center line rise, meeting at 60 degrees, and my center line should be 4 inches. Okay, we are ready to start this layout. First thing we're going to do is locate our element lines on the fitting. Now, if I take this profile of the 10-inch round, and I'm going to take my 10-inch radius as well, and we will locate element lines at the base of my fitting. So I'm just going to connect them now to the base by running perpendicular from these points. This is now where these element lines will land on the fitting itself. This profile is just a half round that's flipped up so I can see the diameter, kind of two views on one. So I have 1, 2, 3, 4 points on the base here. If I extend the element lines from my 5-inch takeoff till they meet my miter, I will have element lines on the miter itself, and the last thing we need is a profile of the sector height. Now, because the sector has a larger radius than the base, the sector is going to be elliptical. Now, I could lay out an ellipse right over top of this, but it gets very confusing simply because the ellipse has to cover 90 degrees. So, in order for me to do that, I would have to lay out a 90 degrees here, create my ellipse, divide it up, and then bring it back to the center line to get accurate measurements. But the trouble is, I still have to lay out this side, and it's going to overlap and be very confusing. So a very simple fix for this is to just take this ellipse and lay it out somewhere else. I choose to do that right here. So let's just make a baseline. And a vertical line. First thing that we're going to do is take what will be our major axes of the ellipse that represents this sector, and we'll just swing that arc on here, and we will also divide it up. Now, the minor axis of this ellipse is the radius of my 10-inch, which is a 5-inch radius. So let's just mark that on there now. And we will divide that up. Now, it's important to me to think about which lines represent what. My major axis represents my horizontal lengths. So we're going to swing these, draw these lines horizontally. So we see now where these lines land on our major axes, where the points will be. And now what we're going to do is get a profile so we can actually see what the shape of that will be, and we'll do that by just extending these lines until they meet their corresponding. And now what I have is this nice little ellipse starting here, 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 and here. This is my sector right here. These points represent where they land on the sector. These distances represent how far these points are from the center line of the sector. And I get the length, how far the points are apart from each other, from this ellipse that we just developed. Well, quarter of an ellipse. Let's just connect those dots. Now that is what my sector would look like, a quarter of it. Oval, half of it actually. Okay, we're ready to do some layout. Now, next thing I want to do is just label this so that I can get my parts figured out. Now, I always like to start with 1 at the base, and then the next point I find would be 2, and the next point I find will be 3, and then 4, and they will end up getting numbered like this: 6, 8, 10, 12, and 14. And I'm going to have 1, 3, 5, 7, and we're going to find the lengths of our points on the sector right here. So from 7, there's 9. From 7, there's 11. So this will go 7, 9, 11, and 13. Now we're just going to lay this out according to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. However, there's one more little trick that we need to be aware of, and that is the fact that our 2, 4, 6, 8, 10, 12, 14 numbers are landing on a miter. These are not the lengths of the actual points that we're looking for. So what that means is I have to lay out this mitered collar, and I have the element line lengths right here. Once I lay it out, then along the curved portion I will find the distance between 2 and 4, 4 and 6, 6 and 8, and that will help me in my layout. So let's go ahead and do that now. And I'm going to lay that out right over top of, partially over top of my ellipse. So I'm just going to stretch this. Parallel line development once again. This will be line 14. I'm going to make it short. Here's 12, 10, 8, 6, 4, and finally 2. We'll lay out a half pattern here. So if I was to take 5 times pi and divide it by 2, I get a stretch out of 7 and 13/16. So using this as part of my pattern, we'll just measure 7 and 13/16. There's my 13/16, and there is my 7. So this here now is my stretch out of my collar, and there's my first point, which would be my 2 point right here. I need to divide this line into 6 equal spaces. Well, let's just extend this one. And let's try the 3/4 scale usually. See if that works. Starting at 0. Oh, and there's 6 right there. So I'm going to start at 0. There's 6. 0 and 6. And I can now divide that into 6 equal parts. 1, 2, 3, 4, 5, and finally 6 right there. And we'll just create parallel lines here, making a grid. And I will have a half a collar pattern. So here's my 4 point, or 14, 15, 10, 8, 6, 4, and 2. There now is a half collar pattern. I like to darken it in so we can see it nice on the page. And there's our half collar pattern. I'm ready to start triangulating. Well, 1 and 2 seems like the best place to start, since I'm going to start by counting. And let's just pick something in the middle of all this that you can still see, and we'll pick a point right about there. I'm going to call that 1. I'm going to head straight up from 1 this far. From 1 to 2 is the true length. It is perpendicular to my plane of vision. They are both on center, so therefore 2 is right there. The 1/12 spacing for my 10-inch is here. Somewhere on this arc will be 0.3. I also need to set up for the spacing. Let's get a better one. There we go. And from 2 to 4, I find right here. There is my 2 to 4 length. So from 2 4 will be somewhere on that arc. So, let's do some triangulating. From 2 to 3, since 2 is on center and 3 is not on center, we will have to triangulate 2 over the full fall of 3. So here's how easy this is. 2 to 3, here is my length of 2, 3, which is not a true length, so I'm going to swing that down to this line here, and now I can triangulate over the full fall. Since 2 is on center and 3 is falling this much, the difference of the falls means that point 3 has a true length right here now. So from 2, I find point 3. From 3, I have to find 4. Okay. What I need to do is, first of all, subtract. How far is 4 from center? 4 is this far from center. I'm finding it using 3. 3 is this far from center. And I need to triangulate over the difference of the falls, which is there. So, I'm going to take our plan length of 34, elevation length I should say, and drop that down. There's my 34. Here now is a true length of 34. The difference between 3 and 4 is fall from center. So from 3 now, I find 0.4. From 3, I find 0.4. And the process starts over again. 2, 4, 4. I have my 1/12 spacing here for my large side. Somewhere on that line will be 0.5. Somewhere on this arc will be 0.5. Get my 1/12 spacing from my 5-inch round, and from now 2 to 3, 3 to 4, double check. There we go. There's my 34. 2 to 4. 4 to 6 is what I'm looking for here. 4 to 6. Somewhere on that arc will be 0.6. Somewhere on this arc, 0.6. We're looking for 0.5 now. Well, first thing I want to do is I'm using 0.3 and 4 to find 5. 4 has a fall from center of this much. I'm going to subtract the 4 from the 5 line. And we're going to take our 45 length and drop it down to the baseline. Triangulate over the difference of the falls. Now, if you haven't been doing this for a lifetime like I have, it's a good idea to document all these points so you don't get confused. From 4, I get 0.5. From 4, I get 0.5. My numbering system here is kind of a fail-safe. If I can count, I should be able to lay this out in order. Here you got to keep track of things. We need to find 0.6. Well, I'm using 5 to find 6. So I'm going to take the fall of 6 right here from center. 6 is that far. Subtract it from 5. There's my 6 length now, and we'll triangulate over the difference. Here is 56 from 5 to 6, drop that down, triangulate over the difference of the falls. Once again, repetition. I have my length for 6. So from 5, I find 0.6. From 5, I find 6. Six or 5 to 7 is this length right here. 1/12 of my 10-inch circumference. Somewhere on that arc will be 0.7. 2, 4, 6. From 6 to 8 is this length here. 6 to 8. From 6, somewhere on this arc is 8. Somewhere on this arc is 8. We're going to find 7. Therefore, I have to subtract the fall of 6 from 7. I'm going to take my 67 length, six to 7, drop that down, triangulate over the difference of the falls. This is the true length here now. From 6, I now locate 7. From 6, I now locate 7. So, I've got a half of my round. This is half of my 10-inch stretch out right here. My next point will be 9 up here. So, here's where it gets fun. My spacings on the top doesn't change. From 6 to 8 is there. Let's find 8 first, I guess. I'm going to take 8. The fall of 8 from center. Triangulate it using 7. So there's my fall of 8 subtracted from 7. Here is my 78 line, right here, 78 line. I'm going to drop that down. 78 is right there, and we're going to triangulate over the difference of those falls once again. There's the true length of 7 to 8. So now from 7, I get 8. From 7, I find 8. From 8 to 10, once again, is my 1/12 spacing. Somewhere on this arc will be 10. Somewhere on this arc will be 10. And now, 9 is our next point. From 7 to 9, we're going to use a chord length that represents the curve from 7 to 9 on our ellipse. So from 7, now it's going to start heading up. I know that from experience. 9 will be somewhere there, and 9 will be somewhere there. Let's just clarify this a little bit. This here would actually be 0.7, 9, 11, and 13, right up to here. That's just, we're looking at them on the surface there now. So let's go back to our drawing here. We have 7 and 8. We got to find 9 next. Okay, so that means I need to subtract my 8 length, which is right here, from my 9 length, which is here. So there's my 8. And we're going to triangulate over the difference of those falls. So from 9 to 8, let's just make this triangle a little bigger here first. I'm now using these triangles here to find out my true lengths. So what I'm going to do is just stretch this line right down into my patterns here. So I have subtracted here's the fall of 8, subtracted from 9. This was an error, obviously. My 98 line is this length on my elevation. There is my 98 right there. 98 lands here. I triangulate over the difference of the falls, meaning here now is the true length of 98. And from 8, I find 9. From 8, I find 9. Let's document that. We now have 0.9. We have 0.9. From 9 to 10, once again, I'm going to take the fall of 10. Here's the fall of 10. I'm going to subtract it from 9. It's this one here we're working with. Now, my 9-10 length is this. There's my 9-10 length. From my 9, I'm going to swing my 10 length, which is here. Oh, looks like I've got to extend that a little more. And now the true length of my 9-10 is right there. There's 9-10. From 9, I get 10. From 9, I find 10. Let's mark that 10. 10. From 10 to 12, once again, is my 1/12 spacing here. So double check that with the start. Happy. From 10, 12 will be somewhere on that arc. From 10, 12 will be somewhere on this arc. From 10 to 11, or 9 to 11, at the bottom, we're going to get that length off of our ellipse or our sector profile. 9 to 11 is there, so from 9, 11 is going to be on this arc somewhere. From 9, 11 will be on this arc somewhere. And we're going to use 10 to find 11, so I'm going to subtract the length, the fall of 10, right here, from 11. Line's right there. Here's our 10-11 length. Length. Triangulate that 10-11 length. Here's my 11 line. 10-11 length over the fall, or the difference of the fall between 10 and 11, which is right there. And now from 10, I locate 11. From 10, I locate point 11. Follow 12 right here. We're going to subtract that from 11. And now I can find 12 from 11 by taking my 11 and 12 length right there. There's my 12 length right there. Triangulated over the difference of the falls is there. And from 11, I now get point 12. From 11, I get point 12. From 12 to 14, once again, is my 1/12 spacing right here. Happy? From 12, 14 will be somewhere there. From 12, 14 will be somewhere there. And from 11, 13, we're going to get that off of the sector profile ellipse right here. So from 11 to 13 is this length. From 11, somewhere on this arc, will be 13. From 11, somewhere on this arc, will be 13. From 12, I need to find 13. Well, 13 is on center. So I need to triangulate 12, 13 over the full fall of 12. Let's do that. Here is my 12, 13 length right here. And since 12 is this far from center and 13 is on center, I can just use this triangle right here. There is my length. And my true length is the full fall of 12 right here. From 12, I find point 13. I'm going to make that nice and dark so I can see it later. From 12, I get 13. Now, 13 to 14, same as 1 to 2. It is perpendicular to our plane of vision, making it a true length. So from 13 now, I get 14. From 13, I get 14. And now we have half of our Y branch built. Now, obviously the procedure is identical for the other half, so I'm not going to go ahead and lay that out, but this here, there's 14 to 13, is an edge. From 14 to 13 is my seam. Seven, 9, 11, 13, this little arc right here is my sector. I'm just going to try and make that 7 down to 1 and back to 7. These points represent my 10-inch round. I got lucky there. So there's my 10-inch round. This here is, well, this is 1/2 of my 10-inch round. This is my sector. This is my seam. And this is my 5-inch round edge. And that we're going to have fun connecting the dots. French curves, flexible curves work real good for this if you haven't been doing it for ever in a day. 7, 9, 11, 13. The trick is to look past 9 to 11. Past 9 to 11. Now I'm looking past 11 to 13. And that's how we draw them in. So, very interesting now. Here's what we need to do. I am going to mark from 7 to 8. And this is just for shop instructions now. If I go from 7 to 8, and 8 to 7 here, I know that I have to roll this part 180 degrees, and I'd have to roll this part 90 degrees. X marks the inside of the fitting. And there we have the symmetrical Y branch. I hope you've enjoyed this. Hit the like, hit the subscribe. I am the Draft Doctor, and this is an asymmetrical Y branch. I hope you enjoy it. Have fun with it. Like I say, this is a very advanced bit of layout. It uses parallel lines, it uses geometric principles, it uses all the techniques we learn in the sheet metal trade. Definitely one of the most difficult layouts that you're going to encounter, and it works. Have a great day.